should move to the next talk by Christian Fischer from the University of Gießen, and he will start the next series of talks, which are non-lattice talks. And Christian will also talk about not with lattice, but with functional methods. So Christian, please go ahead.
Thank you very much. Good morning, everybody. Can you see my screen and hear me very well?
Yeah, it's fine.
Okay, very good. So I thought I started to present you a picture of FAIR. This is the current state of affairs as of September 2020. And I think everybody can clearly see work is going on, and we're looking forward to the time when CBM starts to be operational. So I will talk about fluctuations and the QCD phase diagram, this time from functional methods. I will spend the first part of the talk to kind of summarize what has happened in the past years. I will then briefly explain how hadronic effects play a role in these calculations. There's a new result that we published last year, which is basically the content of the PhD thesis of Pascal Gunkel. And then at the end, I will come back to fluctuations, which is the content of the PhD thesis of Philipp Isserstedt. Much of what I'm telling you today can also be found in this review article that also appeared last year. So this is what we'd like to study in detail, right? The QCD phase diagram as a function of temperature and baryon chemical potential. And whereas this part, roughly, of the phase diagram is very well known from lattice calculations, we currently have to resort to other methods to explore the part with high chemical potential. And that will be the main point of this talk. Of course, one of the most interesting questions, at least for me, is what happens when you go from the physical point in the Columbia plot, what you see here, along the axis of chemical potential, and the question whether at some point you hit this critical surface of second order phase transitions, which then creates a QCD critical endpoint, or you don't. With the lattice, what we definitely can do is you can do extrapolations from the region where you actually can do calculations, which is, for example, the region of imaginary chemical potential, and then extrapolate to the real region and see what you get. And of course, this is a calculation with very well controlled systematics, as we heard before in the previous two talks. What you see here is a result from the Wuppertal-Budapest collaboration from 2015, which shows how the error of this extrapolation rapidly accumulates. So this is basically the error bar. And at some point, the error becomes that large that the calculation simply doesn't make any sense to further continue. What you see also in this plot is our result from 2014. This is the crossover that we find from Dyson-Schwinger equations. That was our critical endpoint at the time and a first order transition region. And much of the remainder of this talk is to explain you how these calculations have been done. And I should also mention that, of course, hot QCD has similar results on this transition line. There's a recent update from Wuppertal-Budapest, which basically shows the same picture. There are several ways to do this extrapolation. I mentioned analytical continuation, but we all know there's several orders of Taylor expansion, which is also possible, and they agree to a certain point, and actually they agree very nicely to even large values of chemical potential. But again, you see how this error accumulates at some point. And again, this is compared here with our result, our latest update from 2019. I think the main result where all approaches so far agree is that there is no critical endpoint for ratios of chemical potential, baryon chemical potential over temperature smaller than, let's say, 2 to 3. And it depends how bold you are, whether it's, well, 2 or rather 3. So how do we do these calculations with functional methods? Well, first of all, we have to see how we determine the order parameters, and we determine these order parameters from the propagators of the gauge fixed theory. So it's rather easy to to extract the quark propagator and correspondingly the quark chemical potential, which as has been mentioned before, then has to be renormalized in a subtractive and a multiplicative way. And we obtain this propagator from the quark Dyson-Schwinger equation. There are others of these equations where we get the others, the gluon propagator and the ghost propagator, and these serve to calculate the Polyakov loop potential, which is then related to the deconfinement transition. Now, of course, the main systematic issue with functional methods is the truncation. You all know that functional methods comprise of an infinite tower of equations, and at some point we have to cut this tower. And of course, the quality of the truncations essentially depend on where you do this cutting. What you see here is the Dyson-Schwinger equation for the quark propagator. Let me just walk you through this. This is the inverse fully dressed quark propagator on the left-hand side, the bare propagator on the right-hand side, and then we have a non-perturbative Feynman diagram which tells you about all possible ways this quark can interact with itself via the emission and absorption of a fully dressed gluon. And we also see the fully dressed quark here, so clearly this is a self-consistency equation. Now, the unknown input into this is the gluon and the quark-gluon vertex. And early calculations in this business used a simple model, a temperature-dependent model for the combined effects of the gluon and the vertex. Now, this is a valuable idea to do exploratory studies, but I would like to argue that it's not good enough to do quantitative or systematic studies. And to my mind, the vital step to that is to include and treat the Young-Mills sector explicitly. So really treat this gluon explicitly, and then going on and treat this gluon vertex explicitly. So what we've been doing for some years, and I will explain that in later transparencies, is doing an ansatz for this vertex, but calculate the gluon then in full glory. And of course, then the next quality step of truncations would be to also include the Dyson-Schwinger equation for the vertex, and actually for all the vertices in the theory. And this way, can step by step by step include more of this infinite tower. Now, in the vacuum, we were quite successful with that strategy. And on Friday in my talk, I will present and discuss with you a truncation in the vacuum, which includes all these vertex equations. Here at finite temperature and chemical potential, we have started to do that. And you will later on Wednesday, I believe, see a talk from Jan Pawlowski, where he explains to you or discusses with you these two works where the vertex Dyson-Schwinger equation actually has already been included. And as I said, this is definitely a next step in the qualities of our truncations. For now, we resort to this system here. So what you see here is the quark Dyson-Schwinger equation for the up-down quark. We work in the isospin symmetric limit, and also a separate equation for the strange quark. And these two are back-coupled to the gluon. We use as a seed the quenched propagator from lattice calculations, a quenched temperature-dependent propagator, and add to this the back-coupling effects due to the up-down and the strange quark. And I will later on actually also show results for adding the charm quark. And in this way, we get the dressed propagator, which is then back-feed into this equation, and this is then solved consistently. Now, this vertex, for all the results I'm showing you in this talk, is built along its Lovelock-Taylor identity and well-known analytical ultraviolet and also infrared behavior from continuum studies. And it has the merit that it's temperature, chemical potential, and quark mass dependent, which suits for a systematic exploration of the Columbia plot. Let me also mention that in this ansatz, there is one parameter built into it, which is kind of a strength parameter of the vertex. And that is adjusted to the lattice results for the critical temp for the crossover temperature at zero chemical potential. So this is not a prediction, but this is actually an input. I'll come to that in the next slides. So let me discuss results at zero chemical potential first, because this is the place where we should show that actually our approach works. What you see here is a comparison of the quark condensate subtracted and multiplicatively renormalized compared to the lattice result of the Wuppertal-Budapest collaboration. As I said, the transition temperature is an input, but what is not an input is the shape of this transition. And if you do the quark mass input right, as we only managed to do in a second go, there was a factor of 2 neglected in the first one, then you actually see that the results from our continuum approach agrees very nicely with the corresponding one from the lattice. So this is the first non-trivial cross-check. The second one is, I explained that we used the quenched gluon propagator from the lattice as an input. What you see here, again as a function of momentum, is the longitudinal part of this gluon. The dashed lines are fits to the lattice input at 3 different temperatures. And then we calculated the unquenched propagator, so including the quark back reaction. And the solid lines here are our results, also for 3 different temperatures. And we did this calculation before the lattice results came out from the Berlin group, Müller-Breusker and collaborators. So the symbols are the unquenched propagator from the lattice. And again, the agreement is actually very nice. Even the temperature ordering, which has been reversed from the quenched one, is gotten right from the functional approach. So with this quality check in a sense, or consistency check in a sense, at zero chemical potential, we went on to do other checks. We checked the heavy quark limit. I don't have time to go into the details here. You can find the details in this publication. And we also went to the Chiral limit in the first exploratory study here. But let me now come to the results at the physical point. So when we switch on chemical potential, we find that at some point this crossover turns into a critical endpoint at these values of temperature and chemical potential, and we find the first order transition. This is again compared with the lattice results from the Wuppertal-Budapest collaboration, and also with a collection of results for the curvature of this transition line, also from lattice calculations. And within the small offset of temperature, as I said, the critical temperature here is an input. So actually, at some point, we should adjust this to the latest results. You can see that up to the point of, let's say, mu t equal 3, there's very good agreement between all the results. You can also compare this with the freeze-out data extracted from experiment. And in the bigger picture, where we have your temperature and chemical potential and all the freeze-out points have been collected by Tatjana Galatyuk, our critical endpoint is roughly here in this region where the freeze-out points seem to bend a little bit, which I find quite interesting. Now, of course, the crucial question is, how reliable is this result and how big is the error of that? And actually, based on the quality checks that we did, at some point we estimated that the error might be of that order. And we will actually see that the improved calculations that Jan will present to us on Wednesday find a critical point roughly here at this point of the QCD phase diagram. So from the combined evidence of functional approach, there's actually also one from the functionalization group, our prediction would be that the critical endpoint exists and is somewhere in this region. Let me also mention that with these simple model approaches that I briefly touched on you would find the critical endpoint more or less in this region, which is actually already excluded from the lattice. So you really need to go beyond this modeling and include the back reaction to the envelope sector to become, let's say, semi-quantitative. Now, I said we can do the same calculation also for the charm quark, and this is what we did. So this is now a 2 + 1 + 1 calculation, and as far as I know, this is the only 2 + 1 + 1 calculation available so far. With probably expected results, the effects are very, very small. So what you see here is the 2 + 1 compared to the 2 + 1 + 1, and you see a slight movement of the critical endpoint, but this is definitely within the error bar of the calculation. So yeah, within these errors, you would actually conclude that there is almost no effect. So that brings me to the second part. of this talk. Let me start with the hadron effects. One of the ways to improve this truncation, as I said, was to include effects in the quark-gluon vertex. And you can isolate in the Dyson-Schwinger equation for the quark-gluon vertex, you can isolate terms which contain off-shell baryons. So contain effects from baryons, actually from mesons, like the pion or a sigma meson, but also for the lowest lying baryon spectrum, effects that reach out into the space-like region where we do our calculation. Now, in an exploratory calculation, my student Christian Welsbacher compared the truncation without and with these baryon effects included. And again, you see that the shifting of the critical endpoint is very small. This was a first trial calculation without taking into account effects of chemical potential in the wave functions of the mesons. We also played around with a parameter that we introduced in order to have a first estimate how big the effects can be. And so this was assuming a quite large mu dependence. And what you actually see is that you can move around this critical endpoint a little bit, but there's no way to move this point to here, 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 or any other place in the QCD phase diagram. So again, the situation is somewhat stable, but we definitely need to explore these effects in more detail. This was one of the main motivations for the study I mentioned at the beginning of this talk from Pascal Gunkel and collaborators, where we now investigated the dependence of these wave functions of baryons, of hadrons, sorry, or actually mesons in this case, at the zero temperature chemical potential axis. And what you should get, this is very well known, what you should get is the silver place property of QCD. Namely, you should not be able to see any changes in observables along this line. And this is precisely what we find. What we show here is the quark chemical potential evaluated at non-vanishing chemical potential and zero temperature. And actually, you see that this is just constant, and this constant goes even into the region between the two spinodal lines of the first order phase transition. And we find the same result for the pion mass, again constant, up to the spinodal region, and the pion decay constant, which constant up until we reach this region. However, this constant, which reflects silver place, is highly non-trivial. When you actually look at the quark propagators and also at the beta-torpedo wave functions, you find that there are partly substantial changes with chemical potential, but these changes compensate each other just in the right way to manifest silver place. And that is very satisfactory to see. And the changes of these wave functions with chemical potential now form the basis of further investigations of these hadronic effects, now also at finite temperature. And finally, we hope to be able at some point to evaluate these effects also on the critical endpoint to that quality. So that brings me to the last part of this talk, fluctuations. Fluctuations, as we all know, are a very, very convenient tool to make predictions and compare with experimental quantities. In particular, it's a tool that hopefully at some point makes it possible to detect the critical endpoint in data extracted from heavy ion collisions. There's a very, very nice review on that issue by Luon and Nushu, which I highly recommend. So the way we introduce this is we have chemical potentials for the conserved quantities, the baryon number, the electromagnetic charge, and strangeness. And these are related to the chemical potentials of the up, down, and strange quark. We calculate susceptibilities by doing the derivatives with respect to these quantities on the partition function. And these quantities are then related to cumulants, which can be extracted from experiments. Now, again, we started this calculation at zero chemical potential to test our results on the level of the truncation scheme that we have at hand. What you see here is a second order derivative with respect to the up quark chemical potential. Our result as a function of temperature is shown as the black curve here. And in red and blue, we have corresponding lattice results from the Wuppertal Budapest and hot QCD collaboration. And what you see is that for temperatures below the pseudocritical temperature for the crossover, we're right in the ballpark of the lattice results. And then at some point for high temperature, the way our results behave, I would say, is not in very good agreement with the lattice. And we can directly track that back to the ansatz that we used for the quark-gluon vertex. So this has to be investigated again for higher quality truncations, which include explicitly the results from the vertex equation. But below TC, we have reasons to believe that our results are actually quite good. Now, this curve shows the results for the second derivative with respect to the baryon chemical potential along the crossover line here. So for different temperatures, as a function of temperature for different chemical potentials, and we go along this crossover line until we reach the critical endpoint. So 495 is almost at the critical endpoint. And you clearly see what you expect. So the very flat curves for small or even semi-large chemical potential become more involved, and finally you find a almost divergency close to the critical endpoint. So there's clearly the signal for the SAP in this quantity. And we can also observe the same quantity along the first order transition line, where you get two results for the second order derivative, one for the chirally broken case, one for the chirally restored case in between the two spinodal lines, which are shown here in this plot. And then at some point, pressure decides which one of these lines is taken, and you get a first order transition from one to the other. Now, two very interesting combinations of these are ratios. One is the so-called skewness, one is the so-called kurtosis. And I plot those here on actually something like a logarithmic scale, again, as a function of temperature for the same points as shown before. So we go along the crossover line and come closer to the critical endpoint. And you clearly see that the closer we come to the critical endpoint, the more variations we see in this observable, until we observe a 1-0 crossing here for the skewness and 2-0 crossings for the kurtosis. Now, when comparing these results with experiment, there are actually a number of caveats. First of all, so far there are caveats on our calculation side. So far, we have only taken flavor diagonal elements in this calculation into account, but we know from lattice calculations at small chemical potential that a flavor off diagonal components should not be neglected. Second, it may be that we detect signs of the critical endpoint a little bit early. There are very nice studies from Schäfer and Bambach within the Polyakov-Meson model, which showed that the more and more fluctuations you include, the smaller this critical region actually becomes. And with the current level of truncations with these ansatz for the quark-gluon vertex, it may very well be the case that our critical region is too small right now. And then, of course, the experimental extraction is not without problems. So these are some of the caveats that you should keep in mind when having a look at the next slide. And this is the last slide before I come to my summary. So here we see the skewness again as a function of chemical potential, and the kurtosis as a function of chemical potential compared with preliminary data which have been released from the STAR collaboration during the beam energy scan. Here you see roughly where the square root of S numbers belong to. The square root of S is also shown up here. And what you see is that actually, so first have a look at the blue curve, which is our result along the transition line. And what you see is that we more or less agree with the experimental data until, let's say, roughly 14.5 square root S. Then for 11.5, the trend is okay. And this last point at 7.7 square root s is clearly off. Now, there are many reasons why this point may be off. As I said, our calculations could be improved. The comparison with experiments surely could be improved. But one of the reasons which I find quite interesting is that it may very well be that for such large values of square root s, the freeze out line and the transition line do not agree with each other anymore, but become separate. And in order to investigate this effect, we also calculated the skewness and the kurtosis along lines which do not follow the crossover line, but are a couple of MeV away from the crossover line. And for the kurtosis, the effect is actually dramatic. If you're as soon as you are a couple of MeV away, the curves change dramatically, and this is related to the rapid changes in this observable. And so this is from along the line. This is 3 MeV away. This is 6 MeV away. This is 9 MeV away. And actually, from this result, you would say that there's even agreement with the experimental data. However, clearly in the skewness, this agreement is far from being good. So there's a lot of work that remains to be done in this comparison. That brings me to my summary slide. I will not go through all these points again. I've explained them in my talk. Let me mention again that we go on with these calculations. Pascal right now has also calculated results for the vector mesons at finite chemical potential, and we have first results also at finite temperature. Philip is currently looking more closely into the issue of thermodynamics and fluctuations, and we're also currently investigating finite volume effects within the PhD thesis of Julian Bernhardt. And with that, thank you very much for your attention.
Okay, Christian, thank you very much for this talk. I think we have a few minutes for questions. Is there somebody? I see here in the chat a question by Winstel. Do you want to ask this question or make a remark?
Yeah, maybe. Maybe this is also for the discussion session, but it's just quite a naive question. So we have seen that you have quite a good agreement with lattice results for the crossover temperature. But however, the susceptibilities, for example, for the quark potentials differ a lot from the lattice results at a certain temperature. And you also already said that you have to improve on truncation schemes here. So again, this is quite a naive question. I don't have any idea of this truncation scheme. So how do you judge the quality of your truncation? So how do you improve on it? And maybe you could give a little bit of insight into this.
Yeah, that's indeed probably something for the discussion session. Yeah. Let me take this opportunity to mention that I will only be able to present at the second half of the discussion session because unfortunately I have to give a lecture in the first part. Okay, so there are several, there's of course one crucial way to improve this calculation, which is to go from, so we started with the 2-point functions, the propagators. We then included results for the 3-point functions, and this is at finite temperature where we are now. On the vacuum, we managed to go beyond that. We included results from the 4-point functions. And what you actually see is something which we like to call apparent convergence. So there's a crucial step in going from 2-point to 3-point functions. If in addition you include 4-point functions, the changes in your results, both in the spectrum and also for the 2-point functions, are actually only on the 5% level, roughly. Then we systematically included even part of higher order correlations, and you again see that corrections become smaller. So it seems to be, as the higher we go into this ladder of Dyson-Schwinger equations, the less the influence is on observables. And this is, of course, something which gives us hope to, at some point, have some really quantitative results there.
Okay, so maybe we can really come back to this in the discussion session.
Yeah.
There's a raised hand here by somebody from Rick, which probably is an experimentalist.
No,
No.
Friedrich, this is Kirill Bugayev. This is just my
why
nick.
do you use a Rick name?
Yeah, well, it's just a tradition.
Okay, good.
I'm working like a collider in my department, you know.
Okay, good. So just ask a question.
Yeah, very simple, but very general question. First of all, thank you, Christian, for your very nice and impressive talk. But then coming back to the short part of your talk, I have a very simple but important question. Can you, in principle, account how the finite volume of the system modifies your predictions for the skewness and kurtosis? Yes or no?
In principle,
In principle.
well, if you ask in principle, the answer clearly is yes.
Good.
We have not yet done the calculation, but we are right on our way there. So as I briefly mentioned, my student, Julian Bernhard, is looking into this. And we have already first results on the volume effects on the critical endpoint, which have to be further studies and substantiated. And we definitely plan then as a next step to look into the volume effects of the susceptibilities, of the fluctuations. Yeah.
Thank you very much.
Okay.
I'm looking for your results.
Okay, I guess we can discuss this also a bit more in the discussion session. Unfortunately, we have to postpone the other questions. There are still two around also for the discussion session.